lots of momentum. I'll write it out a little bit, because if I say COM, I think I meant center of mass. Anyway, concentration of momentum, what do I mean? I mean that I write down all the momentum in the problem final minus all the momentum in the problem initial equals, and it's often going to be 0 as it was here, but if there's external forces, right? And it would be work if this were energy, but it's not work. This is momentum. So I need a thing that's called J, which is a vector quantity in general. Has to be, because we're talking about differences in momentum, right? It's the impulse. The impulse is just the change in momentum of the system. That's all it is. In the same way that the work is the change in energy in the system. You get a little bit in trouble there because there's actually, as we'll see later in the class, there's multiple ways of adding energy to a system. You can do work, but you can also heat it up, right? You can add heat to the system. For momentum, I'm racking my brain right now. I'm pretty sure, though, that impulse really is defined as the change in momentum. I don't think there's another way. Like if the momentum changes, it has the impulse given by the change in momentum. So you don't have to worry about some other way momentum could have changed. So this really is the thing to put on the right side of the equation. You don't have to worry about heat. It's always just going to, or something analogous to heat. And I'll put down here external. You don't have to worry about external, about the part of the impulse is due to external forces. And so there's two ways to think about that. Then one is to think about it in terms of change of the momentum. And we can write it out, though, this way. We can say J equals, all right, I just said change of momentum, right, and that equals an integral of the force, the external. So if I want the external, I should be careful. No, this is okay. This is okay. So if this is my closed system, then it's only external forces I need to worry about. That's fine. I'm okay to write external like this. But we can make it more general and not do that. That's okay. Let's do that. This is a general function of time. Doesn't have to be, but just I'm being general for my integral here. Times dt. So remember the definition of work, right? Work was F times something, but it wasn't times a time. What was it times? A distance. So when you exert a force, so some external force is exerted on an object, right? The object can acquire energy as a result because of the work done. How do you calculate it? Well, it's just force times the distance for constant force. This is not constant, you've got an integral. We'll say here, if it's constant force, right, then you'd say, oh yeah, well then J is just equal to the whatever force it is you're exerting on it times delta t. So it is. This is not a dot product, right? Because this thing's a vector, that's a vector, this thing's a number. I'm just multiplying a number by a vector to get a vector, right? Unlike with work we took a force, which was a vector, and took a dot product with the displacement, with that delta r, right? So this is subtly different. Time is a number, it's a scalar. So we multiply time by the force, we get a vector out. But that's what we do need because, in fact, a change in momentum, well, momentum is a vector, so a change in momentum is a vector. Any questions about this? I see hands up. I guess you're working it out. All right, good. All right, so then in general, what do we have? We have this, and that's how we figured it out. Yeah, if you have a big change in one guy's velocity and not the other, then the one whose momentum was, the one whose velocity was a bigger change probably corresponds to a smaller, what did I say, mass? Yeah. All right, so what are the consequences? I'm gonna do a couple qualitative things with pictures, and then we'll do a few demos and be more quantitative. So the book's got a nice picture I really like it. If you're looking at the outside of a train car, right, and the train car is initially still, but then it moves. Well, you know something's up, right? When the train car is moving, it means something inside is probably moving. It's probably pretty big, right? So here's the train car. Here's its initial position. And let's say the train car starts there, but then after the you see it move, it's moved over. So I'm going to do is I'm going to draw two pictures, before and after. Here's time 0, and then down here's time 1. And at time 1, maybe the car, let's see, I guess I'll draw it this way. So at time 1, the car's moved over. If I do this properly, the car's the same length. This isn't relativity. I'm getting shorter or longer. All right, good. So there's my train car. It's moved over. So if this car moved over to the right, so this is initial and this is later. So T final or T initial and T final, right? So if there's something inside that's walking around, and if there's no friction, suppose this is a really efficient, very nicely built train, and it's not there's no rusty wheels here or whatever. So there's no horizontal force due to friction. And that means there's no external force, right? It's not hooked up to anything. This guy's not hooked up to the rest of the train. It's just sitting on the track. So the only forces involved here are the internal forces. There's some other than down to the gravity up to the normal force from the track, right? So which way if there's some object inside, suppose a big elephant inside, which way did the elephant have to walk for you to see the train car move to the right? Based on these ideas over here of the center of mass not moving. Center of mass isn't moving in the beginning. Train's holding still, the elephant's holding still. Then the elephant starts to walk. Either goes this way or that way. Which way do you have to walk for the train to have gone that way? So to your right. I'm getting both rights and lefts. Who thinks that the elephant had to walk to the right? Who thinks the elephant had to walk to the left? The lefts have it. But of course, you don't vote for the answer. That's correct. So let's see if we can see what that looks like. So if you think go to the left and still stay inside, I think to myself a lot of room. You better be over here. Oh, this is backwards from the way I do it before. So I've got my little elephant, and he's got his, his funny feet. All right. I just crammed him in the back. Here he is. He's sticking out the back of the train. He had to go that way for the train to come this way. Why? Because the center of mass of the system didn't move the whole time. How do I know that? Because there's no external force, F equals ma, where m is the capital M, including the mass of the elephant, the mass of the train car. And the way it's drawn in the book, so the way I do it in the book is that the elephant goes further. So the elephant moves, actually, the picture in the book is flipped. I just go backwards because I'm capricious, but right away. But the elephant, they have the elephant going further than the train car. So if that's what happens, if the elephant walks, and at the end of the day, after he's done his walk, if he is displaced by more than the train, which is more massive, the train car or the elephant? So like right here, which one went further, the little ball or the big ball? The little ball. Which is more massive, the little ball or the big ball? The big ball. So if the elephant had moved further, if he had, so here's how far the train car went. Here's the center of mass of the train right here. Right? Center of mass for train. It's right here, in the center of this car. Where is it down here? It's same place, right? Oh, excuse me, same place relative to the train, not same place in space. Here's my x-axis, right? Not my x-axis is fixed to the ground, right? I'm saying, oh look, my center of mass of the train moved to the right by some distance. It started off over here, wound up over here. So that's how far it moved, right? Delta r center of mass train, right? I call it x. Delta x center of mass train, right? So that means that he had to go that way. We know that. And if we knew that he were the same mass as the train car, he would have had to go the same distance to the right. So you have to get his center mass is here, but he wound up outside the train. So that doesn't work. So maybe if he only goes a short distance, that means that he must be more massive than the train car. Does everyone see that? Which is not realistic for an elephant. So that'd be a woolly mammoth. All right, probably mammoth. All right, there he is. Yeah, oh, he's got big. Oh yeah. All right, good. All right. Oh, little tiny ears, right? They got big woolly legs and they kind of hunchback. They're hunchback and they have a little funny tail and they're woolly. Okay, so there he is. Woolly. We need a bigger animal. And people stay awake when I draw pictures. Good. This class, I have these things going. I think these are delightful. These little, air tracks and stuff. Students just crash. If I draw a woolly mammoth, wake up. So all right, woolly mammoth. Right? So there's a woolly mammoth. He has to be big in order to, so well, assume it's the same drawing up here. I'm trying to make him the same mass as before. So he just moved a shorter distance. He started here, he ended here. So that's a smaller distance. right? And it's in the opposite direction. Center of mass didn't move. More massive, smaller displacement, less massive, bigger displacement, opposite direction. When the dust clears, center of mass didn't move. If it did, if you went through the calculations and said, wow, the center of mass is different here than it is here, you know there must be some external force in the problem, right? There must have been somebody over here pushing on the train from outside, or whatever, magnet, something, right? Okay, great. So that's sort of, this is related to this. In this case, I wasn't talking about velocity. It's not the ultimate displacement, but it's the same basic idea, right? That no matter what happened, no matter how, I didn't even talk at all about how fast the elephant moved. Doesn't matter how fast you did it. Doesn't matter if it took him a minute or an hour. At the end of the day, after he's done his motion, this must be the final outcome. If you know how far he moved, you can figure out how far the train must have gone, right? Because we're using symmetry arguments. We're using this law. I don't have to worry about the details of how he moved over. Oh yeah, and then real quick, I'll do another one for fun. I already drew a picture over here of a U and said, where's the center of mass? Right? And we decided it was below the object. It's down here somewhere, right? So people can do this too. And that's how, so there was a revolution in high jump. Who knows what this is called? It's somebody very flop. Who is that? Fosbury? I apologize to Fosbury or whatever his or her name is. But yeah, I think that's right. It's something very flop. And the idea is people used to do high jump, they jump over, sort of dive over, or maybe I forget if he went feet first or not. He used to do all kinds of crazy things. But this guy figured out, I think it was a man, figured out that he'd run toward the high jump and jump backward head first and arch his back in a funny way. And this gave him an edge over competitors. It was a better strategy. What was he doing? Well, the picture's in the book. I'll draw it real quick. So here's his hand, right? He's got his arm over here. So here's the thing. He's going head first, right? It's a really strange perspective. He's arching his back. Here's his chest, right? He's arching his back to go over, and his arm comes down like this, right? So here's his hand down here. Here's his head. He's facing away from us, right? Along here, right? He's got his shoulder over. Just so it's clear what's going on. And here's his, behind, and here's his knees, right? And his legs are coming back like this, right? It's a little misshapen. You see what I'm saying? He's doing this. Oh, he's wearing shorts. That's awful. That's not intentional. Here he goes. All right. I go too far. I get in trouble. All right. So here's what he's doing. And he's got a funny hand. Here's his hand. All right. And where's the bar? The bar's going like this, right? He's right up. His body is close to the bar. Does everyone see that? So where's the center of mass? It's down here. His center of mass is below the bar. Does everyone see that? And what path did the center of mass take? Once he leaves the ground, what path is the center of mass following? Straight line. Parallel parabola. That's right. So his center of mass did this. At no point did it go over the bar. But because he's got this clever technique that allows him to make a U out of his body, right? Then he's able to set it up so that every point along the way, right? Got lots of hair this guy. Every point along the way, he's able to keep his body, so the part that's lined up, along the x-axis is perpendicular to the plane of this thing, right? Whatever part of his body's there, he holds up relative to his center of mass. How does he do it? He holds other parts down. So the trick to this technique is you always have your limbs as far down as you can put them, right? So, and there's obviously constraints on the human body, and it turns out that the best way to do this, right, is to do it back first, which I wouldn't have guessed. I would have thought it's better to do it like this, right? But it turns out it just gives you more. There's also the issue of how much spring you get for the different angle and all this stuff. But ultimately, what you need is a U shape, and that allows your center of mass to always be below the bar, and you can get an extra foot out of it, and you get gold medal and the rest of it. Right? So it's really it's useful, to study physics for the Olympics. And then the other example that my wife likes is, so I'm more of an opera guy. She's more. I mean, I don't do it. I like to go watch it. But she's more into dance. So she likes to watch. And my daughter loves ballet. Right? She sleeps in her ballet outfit and all that stuff. Anyway, no, it is nice. It's wonderful. So she's kind of like it anyway. So I don't know, it's very popular these days, I guess. So she's going from left to right. Not my daughter. I'm a real dancer. What do? They want to look elegant, right? So how does the ballerina beat physics, and actually look elegant? Because once she leaves the ground, she's forced to follow a parabola, right? Well, her head. So let's just draw her head. What she wants is it's a very simple head. They smile too low. And they don't have long hair. I'm gonna draw long hair, so it's clear where she's going. She's going that way, right? She wants to do this. She wants to look like she's not changing her height relative to the ground, right? It's just and then just glide. It's very painful doing this. And then she winds up over here, right? So that's what she wants to do, right? She's a little less happy over here. How does she do it? Her arms don't move. So that's a little thinner neck than that. And her arms go out, right? Her arms are straight to the side, right? So she's very muscular. These people are muscular, right? And she's got her tutu, right? You know what I'm talking about? She's going that way. Now she starts off with one leg down, right? She's got one leg down. She's in good shape. She has one leg down, and she's on point, right? But this leg is up. This is important. This leg is up. That's instead of beefy, right? So she's going that way. But where's her center of mass? Now her center of mass right here, somewhere down here, because most of her mass is like through the trunk and the legs, right? I drew her a little big on the upper, but she's got a linebacker up here. But they're usually much thinner on the upper part of the body. So that means the center of mass is like right here. Now it's got to go up, right? Center of mass has to rise and come back down. She's leaving the ground. Here's the ground, right? How does she do it? Well, when she's over here, right? Her arms are at the same height, let's say. Okay, all right, and kind of all belt and the rest of it. And then she's okay. All right. So the way she does it is both legs are up. So when you come over here, she's got her torso is almost exactly. Here's a tutu. Her torso is almost exactly the same spot, but her legs are up, right? And so that allows her to have a wow. Really good. You get the idea. It's just fun to draw pictures instead of do the algebra. But yeah, so this is what she's doing in the middle. Her center of mass is higher now because she raised one leg. That's really the only major change in her posture. Is her leg went up. And then over here, same thing. She touches down with the right leg. Okay, well, you get the idea. There's arms that comes down. Okay, there's two. And then there's the legs. And the legs are what's important. This leg comes down, right? And she's touching the ground again, right? So the way it works is that you can. And I'm not going to do the basketball player. You can guess what that looks like. You guys know who Michael Jordan is? That's before your time. Yeah. Okay. He's a computer scientist on campus. He's an extremely smart man. And there's a basketball player as well named Michael Jordan. And it's true though. I know much more about that than Michael Jordan. But the Michael Jordan basketball player was master. He was a very strong jumper among other things. And he was talented beyond belief. I can't. There's a lot of things you can do that I won't describe you, of course. But one of the things I would notice, because I'm not a sports fan, my brothers, my parents watch. I come in the room and I was like, he's beating the laws of physics. But what's going on is that I now have to watch sports now. But the result was the same kind of thing. So this is easy to see because it's a very specific posture. What he did, he's moving all his limbs and it's really hard to figure out what he's doing. But if you watch, he starts to jump, he's leaving the ground, he's he makes his opponent think he's cresting, that he's reached the top of his parabola. How does he do it? Because he starts crouching, starts bringing his legs up, right? So now his head starts coming back down, but his head's not coming back down because he's at the top of his parabola. His center of mass is still rising, right? So he does this, he's crouching, but then he has a second wind, so his head does this, right? And everybody's already exhausted, so they've jumped up and waved their hands around, and they've already landed and gone home and had dinner. He's going up for a second, So the way that works is he crouches and does that, essentially. But it's more complicated, you have to get a grease pencil, and that's how some meetings they go through and find out where his center of mass is. Anyway, so that's the basic idea. And there's a lot of things. This accounts for a lot of stuff, right? Lots of sports, lots of dance, lots of things. How people can, because they're constrained. F equals ma, center of mass has to obey a parabola. The only exception there is if you're interacting with other people, so somebody can push you when you're in the air. Also, if you have a ball in the game, right? Somebody tosses you the ball and you catch the ball, then you're not on the same parabola anymore. Unless, from the outset of the problem, you consider the ball that's flying towards you and your body as the same system, right? In that case, when you catch the ball, you're still, as a system, following the same old parabola as you were before, right? But your body changes direction a little bit because, if you consider the body by itself without the ball, that's not following the same parabola. And so here's some more demos along these lines. Maybe we'll do this real quick. You guys know how these things work. So there's two things that are being, so now we're getting to collisions. We talked about collisions here. We're going to do some collisions over here in a second. I think you'll do some in your labs of various types. So you know how this thing works, right? How many balls come out the other end when I let this go? Yeah, that's right. This guy just bounce on one side or something. This guy comes off the other side. And so the way you know that must be what's going to happen is that two things are being conserved if we were to do the calculation. So this will drive crazy if I let go. And you know what happens if I do two balls? You know what happens? Two balls, yeah. The one that's always kind of weird to me, even though I can do the calculation, is if I do four balls. What happens now if I do four balls? So it seems like what's going to happen is it's going to plow through and all the balls fly out the other side, right? But that's not what happens, right? What happens? Oops, I'll keep it still. Oh, let's see. All right, let's see what happens. There it is. One of them is just left behind, right? You guys have this in your desk, right? Oh, and now what's happening is there's all kinds of stuff. Okay, there's all kinds of things happening here. But if this is a perfect situation, it almost is. And by perfect, what do I mean? I mean that the collisions are elastic. That's the word I haven't used in class yet. These are examples of very good approximations to elastic collisions. And if I start off in a situation where only one of these guys has non-zero velocity, it turns out the only way I can satisfy conservation of kinetic energy, which is conserved for elastic collisions, as we'll talk about the rest of class, and if you're going to conserve momentum. So momentum is always conserved. You can see right off the bat that this conserves momentum, right? If this guy comes in at a single ball, and then this guy comes off at the same velocity, right? That conserves momentum, m times v. Well, these all have the same mass, same m, right? This guy has some initial velocity v, whatever it was, a tenth of a meter per second, or I don't know how this is going, something like that. Well, then after the collision, we know that momentum, so if there's no external force, right? If there's no impulse acting on the system, then this guy flies out with the same velocity. Then that means it's mv. Okay, momentum's conserved. We had one mv initially. We got one mv at the final stage. But you might say, yeah, but there's other ways I could have conserved momentum. I could have had these two guys come off at half v, right? Because now you got 2 times the mass, but you got half the velocity. 2m times half v is mv. So if I started with mv, that would also, so there's many different solutions for conservation of momentum that work. But if you're going to conserve kinetic energy and conserve momentum, now you're constrained. You have to satisfy conservation of kinetic energy and conservation of momentum. Those two things, those are different conservation laws, and you can see that right away, right? Because kinetic energy goes like v squared, momentum just goes like v. So they have different functional forms. If you satisfy both of those constraints at the same time, and right away we can see that this makes sense, right? This guy's coming in at velocity v. Then what's the kinetic energy initially? These guys aren't moving, they don't contribute. But this guy's kinetic energy, what is it? It's 1/2 mv squared. Right, that's right. And then after the fact, okay, this is 1/2 mv squared. It's conserved. But now consider what happens. It's supposed to be considered another solution that satisfies momentum conservation. So now I've got two guys flying out, and they're both going at half v. But there's 2m. If I ask what's the kinetic energy to that, I'd say, well, it's 2m times 1/2 squared times m squared. Well, a half squared is a quarter, right? So now you get an extra factor of a half. So there's actually less kinetic energy in this case by a factor of 2 than there was for this guy coming in. If these guys leave at half the velocity he came in at, which I needed to do to satisfy conservation of momentum. So I just talked that through without doing algebra on the board. I don't know if that was hard to follow or easier to follow, but I just want to show you a couple different ways because it's pretty useful, pretty important concept for the class. So the idea is that, in general, it's always true that momentum is conserved in any closed system. Now, if there's external forces acting on the system, then you need this J, right? So momentum conserved. M1 v1 plus M2 v2 plus M3 v3, right? I didn't actually write it down explicitly. Let me do that. So, M object 1 v1 plus all the different momentum, right? And then there's M1 v1 plus and so on. And these are for different moments in time. So this is all for time final and this is time initial. So I indicated that out here. I can put that here too. It's one final and this is one initial for the velocity. The masses are changing to the velocities. This equals 0 if there's no external force, as was the case here. Now it's also true that energy is always conserved. That's a rock solid physics law. Energy is always conserved. But the thing is, there's lots of forms of energy. Some are easier to measure than others in a situation like this. Kinetic energy is pretty easy to keep track of. All you know is how fast things are moving, what their masses are, right? But there's other kinds of energy. When these balls clack together, they make an audible sound, right? That costs a little bit of energy. So in fact, that's part of why I feel these guys bang back and forth after a while that they get lower and lower in amplitude and it takes pictures away, right? It's because the energy is being lost, partially to sound, but it also is lost to something else. Where's most of the energy going in collisions? If not to kinetic energy, where's it go? Heat, yeah, warming stuff up. So heat, you wind up generating heat, and the temperature goes up. And temperature and heat aren't the same things. I think most of you know, and we'll see that in greater depth later in the course. You get the thermodynamics, you do a proper treatment of heat. But for right now, what matters is that you're aware of the fact that when you've got friction, right? Or when you've got other types of dissipative forces, like if you bang these balls, the balls deform a little bit. They're springs, right? They're solid steel, but they compress a little bit. And in the process of compressing, they actually wind up, it's like a frictional force inside. So some of the compression, which is like a potential energy of a spring, right? Some of that gets converted into heat and warming the thing up. And that's what happens. But this is close enough to conserving kinetic energy, so that the energy is being transferred from the motion of this ball ultimately into the motion of this ball with nothing else, with only a tiny amount of heat loss or something, right? Tiny amount of loss of heat. We call it. What did I say it was? It's I already lost the word. Elastic. It's an elastic collision. Now there are inelastic collisions. In fact, most collisions in the world are inelastic. Unfortunately, if I bump my car against somebody else's car, if I go slow enough, it's an elastic collision. If it happens too fast, right, then it's an